the basic facts about intersection theory that I described yesterday. And there are more things that I should have said and didn't. They require a fairly substantial proof. Certainly the existence of an intersection, a well-defined intersection product. As I said, it's a vast generalization of Bézier, and I did not prove a word of it. And I'm not going to. I can give you a reference, and I will. There are a lot of them, and what I will do is I will talk about the various ways of setting up an intersectional theory. But as I said last time, what I want to do today is just get started using it and see how it comes up in the course of algebraic geometry. In some ways, I feel like a child who's been given a wonderful new toy for their birthday, and they want to just go ahead and play with it, but their parents insist that before you play with the toy, you have to read the instruction manual. And it's 70 pages of fine print. We're not going to read the instruction manual. We're just going to... So this is, I'm going to take this as a sort of paradigm for the sort of problem that we're going to be trying to solve here. It's a fairly natural problem when we talk about something you can almost visualize, except for the fact that when I say P3, I mean P3 over the complex numbers rather than over the reals. But apart from that, this is a very visualizable problem. If you just draw 4 lines, unfortunately this blackboard does not accommodate 3 dimensions, but it's, for one thing, the P3 is really unnecessary. If I phrase the same question in A3, it would have the same answer, but if you think about it, for 4 general lines, none of the lines that actually meet all 4 are going to lie in the hyperplane at infinity or even meet these 4 at points at infinity. So you could really think about the problem completely without losing anything. You could think about the problem just in 3 space. And if you're willing to work over the real numbers rather than the complex, then you can actually imagine the problem. So, of course, in keeping with Robin's dictum of mentioning twisted cubics at least once in every lecture, I have to give you this variant of the problem. Suppose instead of specifying 4 lines, I specify 4 twisted cubics randomly placed in 3 space. And I ask the same question: how many lines are there that meet all 4? Now, the answer really is not so approachable. And I want to suggest this, there are lots of ways of answering this question. There are fewer distinct ways of answering this one. But we're going to do it in any case. So how do we approach a problem like this? Well, this involves a series of steps that are pretty much standard in every problem in enumerative geometry. The first step, and this is really the way we think about the problem, we introduce a parameter space. For the objects we seek. Now in this case, we're looking for lines. We're looking for lines that satisfy some conditions, either meeting 4 lines or meeting 4 twisted cubics, or you can imagine lots of other conditions we could impose. But basically, the set of objects we're looking for is a set of lines in P3. And what we'd like to do, and this is very much in keeping with what Robin talked about yesterday, is to describe a parameter space for these objects. In other words, this is a priori just a set, but in fact, it's not surprising, given what Robin said, that in fact you can associate to these, in a natural way, you can associate to the points of this set, the elements of the set, the points of a variety. And that is the Grassmannian of lines, which we'll talk about. One of the first things we have to do in this step is to actually describe the Grassmannian of lines. So this will be this parameter space. In fact, also, Robin mentioned Hilbert schemes, and he mentioned one very basic concrete example of a Hilbert scheme. If you look at all conics in P2, he showed that the Hilbert scheme parameterizing them is just P5 in an obvious way. And more generally, you can do that for hypersurfaces of any degree in any projective space. in some sense, this is the second most basic example of a Hilbert scheme, or the most elementary. The idea that we can parameterize the set of linear spaces in projective space by the points of a scheme, again, the Grassmannian. This is another example of a Hilbert scheme. Okay, so that's the first step. Now, as I said, this is sort of the way we think about the problem. The idea is once we think of the set of lines in P3 as the points of a variety, then we can ask, what is the subset? How can we describe the subset of lines meeting a given line? So we just draw that as sort of a subvariety, which in fact it is. It's just to say lines meeting L1. And we have likewise a subvariety of lines meeting L2 and lines meeting L3 and lines meeting L4. And what are we asking for? We're asking for what are the number, how many points of intersection are there of those four subvarieties? And that's exactly what intersection theory is set up to answer. It tells us if we have a collection of subvarieties of a given variety, and we ask in how many points do they intersect, again assuming the usual transversality, the intersection theory gives us a sort of a process by which we can try to answer that. And the first step of the process, I'm going to call the Grassmannian G. And we'll go through all these in the remainder of the lecture. We're going to calculate the Chow ring. In other words, the basic theorem that we had on the board yesterday says that the number of points of intersection depends only on the classes of the subvarieties we're intersecting. In the Chow ring, we first need, in order to use that fact, in order to calculate, we need to have a description of that ring. I said yesterday that in general, these are not calculable. Luckily, this is one of the exceptions. We will actually be able to describe the Chow ring of the Grassmannian completely and in fairly short order. Well, of course, once we know the Chow ring, the next question is find the class of the subvarieties. So find the class of the subvarieties of G corresponding to the conditions that we impose. So here we have lines meeting L1. That is a subvariety of the Grassmannian. We want to find its class. Let's call it sigma, say. And not unreasonably, since we can move any line to any other, these are all belong to the same class. So we have arbitrary four subvarieties whose intersection we want to calculate, but they all have the same class. If I have two lines in P3, I can sort of interpolate between them with a rationally parameterized family of lines. That gives me a family of cycles in the Grassmannian, parameterized by P1. That says that the cycle of lines meeting a given line, the class of that cycle is independent of the choice of line. So the final step then is just to calculate the product. In this case, sigma to the fourth. And that's in this ring A of G. So that's our paradigm, and we'll see this sort of pattern repeated over and over. I'll give you some more examples as we go along, but this is the basic idea. The one point to take away from this is an observation that when we apply intersection theory, when we describe intersection theory in the abstract, we say, let X be an arbitrary smooth projective variety. But in practice, when we apply it to answer problems, concrete problems in algebraic geometry like these, we typically apply intersection theory to parameter spaces. Parameter spaces are fundamental in this subject because it's by applying intersection theory to parameter spaces that we answer these sort of geometric questions. And we'll have another lecture later in the week in which we talk about the sort of art of constructing the right parameter space for a given problem. Okay, so having said all that, let's get to business, and let me talk for just a few minutes about Grassmannians in general. So we need to establish, if nothing else, some notation, some language, and we can talk about these objects. So this will be the next topic, Grassmannians. And Grassmannians are very simple. GKN is defined to be just a set of k-planes, k-dimensional subspaces in an n-dimensional vector space. And there's already one little bit of language and terminology I should introduce. We can also associate to a k-plane in Cn a k-1 projector space, linear subspace of projector space Pn-1. So we can also look at the Grassmannian, say, which we denote with a blackboard bold symbol, GKN, which is the set of k-planes, pk sitting inside Pn. That is the same thing as gk plus 1 n plus 1. In other words, linear subspaces of dimension k plus 1 in an n plus 1 dimensional vector space. So now the problem is, you say, why not just be consistent and use one notation or the other? The reason is simply that when we talk about Grassmannians in general, this is much more often the easier notation to use, the more intuitively clear. On the other hand, when we talk about a particular example, like for example today we're going to be talking about the Grassmannian of lines in P3, we could write the Grassmannian of lines in P3 either as the Grassmannian of two-dimensional vector subspaces of a four-dimensional vector space, or, again, lines in a three-dimensional projector space. Which one would you rather try to visualize? And the point is, when we're talking about a specific Grassmannian, it often makes sense to use the projective notation because it's just you gain one precious dimension in your ability to see what's going on. If I just a moment ago, I had on the board a picture of 4 lines in 3 space. Modulo the fact that the board doesn't really adequately represent 3 space, you could sort of see what I was talking about. Whereas if I tried to draw 2 planes in a 4-dimensional vector space, it would have been, well, worse. Anyway, so that's the problem. We're going to use both symbols, but for now, since we're talking about Grassmannians in general, I want to focus on the vector space notation. Okay, so this is a priori just a set. In order to give it the structure of a variety, and it has one in a natural way, what I'm going to do is look at the Plücker in that. So I'm going to think of this as a set, and what I'm going to do is embed this set as a subset of the projectivization of the kth exterior power of Cn. But the map, this is again just a set map for now, sends a subspace, V, let's say, which is the span of vectors V1 up to Vk. I'm going to associate to that the wedge product of these basis vectors. Now, obviously, there are a lot of different bases for a given vector space, but as you know, if I chose a different basis, the wedge product of the basis elements would be the same up to multiplication by the determinant of the change of basis matrix. So up to scalars, this is a well-defined vector in which KCN, or equivalently, this is a well-defined point in the projective space. So that gives me an inclusion of sets. And now I'm going to simply assert that in fact the image of this is a variety. It's the zero locus of a collection of homogeneous polynomial equations. So let me just say that. Image is the zero locus of a collection of, in fact, we can be specific, of quadratic polynomials and these are called the Plücker relations. I apologize for mispronouncing the name that I had. In other words, if I look at a general member of this vector space, right, it's expressible as a sum or linear combination of vectors of this form. But the set of vectors in here that are expressible in this way, totally decomposable, that the characterization of such vectors is via a collection of quadratic polynomials. Let me be a little bit more concrete here, if you don't mind. Because it's useful, and I don't want this to sound like a very abstract thing. More concretely, if I write this subspace V in Cn, this k-dimensional vector space, can be represented as the row space of a matrix n, a k by n matrix. So A11 up to A1n, AK1 up to AKn. So I can represent the linear subspace as the row space, this, the span of the rows of a matrix like this. And the map, the Plücker embedding in this case, we send this to the homogeneous vector, which is given by the minors. So V goes to the collection of, well, I should say maximal minors, or k by k minors of n. And again, obviously there are a lot of different matrices that represent the same linear subspace, which have the same row space, but they all differ by multiplication on the left by an element, an invertible k by k matrix. And the effect of multiplying on the left by a k by k matrix, invertible k by k matrix, is simply to multiply all the minors simultaneously by the determinant of the matrix. So up to scalars, this is a well-defined vector. So okay, so that's the Plücker embedding. And I want to use this matrix again in a moment, so hold on to it. Yeah, in fact, I want to use it right now. So the claim, in fact, I'm going to erase this paradigm. And so the claim is that, in fact, this locus GKN sitting inside the projector space is a smooth projector variety. It's smooth of dimension k times n minus k. And the proof is, this is something you can see pretty much directly, if k, let's say gamma, rather, is a n minus k plane in Cn, and we look at the set of k-planes which are complementary to gamma. So lambda intersect gamma is just the zero subspace. Okay? This is an open subset of the Grassmannian. In fact, you can see in the projector space in which it sits, it's just the complement of a hyperplane section. So it's, in any case, an open subset. And the point is that I claim that this again is just a claim for now, that this is isomorphic to affine space of dimension k times n minus k. And the reason is, we can go back to this matrix and, for example, if gamma is just the locus where the first k coordinates vanish, so x1 equals xk equals 0, then this open subset is just the locus where the first k by k minor is non-zero. So in that case, u gamma is the set of essentially v, such that the first k by k minor of m is non-zero. Now, if I know that the first k by k minor is non-zero, then I can multiply on the left by the inverse of that first k by k submatrix. And I arrive at a unique expression of V as the row space of a matrix which has the particular form where the first k by k block is just the identity matrix. B11 to B1n minus k, bk1 bkn minus k. In other words, for every such k by n minus k matrix here, I can take the row space of this matrix and get a k-dimensional subspace complementary to gamma, to this particular gamma, and conversely. So every plane complementary to gamma is represented uniquely in this form. And of course you have to check that this gives, in fact, a biregular isomorphism of this open subset with affine space, but it does. So the Grassmannian, this is important because remember, in our approach to intersection theory, via the moving lemma and so on, we are restricted to working with smooth projective varieties. And so we have to know that the Grassmannian, if we're going to be applying this theory, is in fact smooth and projective. It is. Okay, so now I want to erase the boards again and focus on the Grassmannian of interest to us, which is just lines in free space. And now we get very concrete, or relatively concrete. And I don't know about you, but my powers of visualizing a four-dimensional variety may not be great, but they're better than my powers of visualizing a k by n, k times n minus k dimensional variety. So let's focus on that one. So now, again, focus on, we're going to switch to the projective notation. And so again, that's the lines in P3. The second step of our paradigm, which is now erased, was, now that we have some assurance that this is in fact a smooth projective variety. In fact, in this case, I should say, this sits naturally, this is a four-dimensional variety, and it sits naturally inside the projectivization of wedge 2 of a four-dimensional vector space. That's just P5. So it's just a quadric hypersurface in P5, and a lot of the geometry of G13 can be viewed in terms of that embedding. But I'm not going to take that approach. I just want to point out that this is just sort of at the margins of what you can fool yourself into thinking you can see. Okay. The second step of the paradigm is to describe the intersection ring, the Chow ring of this variety. And to do that, I want to start by showing you some cycles. I need a set of generators to start with, and I'm going to describe those now. And then we're going to prove that those, in fact, freely generate the Chow. It's this thing, in some sense, you can think of this as a sort of generalization, or by analogy, similar to taking projector space and taking just linear subspaces, one linear subspace at each dimension. What I want to do here is I want to fix what's called a flag, which is to say just a sequence of linear subspaces of P3. So that'll be a point contained in a line, contained in a plane, contained in P3. And the picture here is just the obvious one. I have a point, P, I have a line, L, and that sits inside a plane H, and all of this is sitting inside P3. Now I want to introduce the following cycles. The biggest cycle in some sense is what I'm going to call sigma 1, which is the set of lines, lambda, that intersect L, that meet L. Okay? That is a subvariety. If it's not obvious, you could observe, of course I've erased it now, that this is just the complement of one of the open sets I introduced a moment ago. In other words, this is a hyperplane section of the Grassmannian in P5. But in general, I mean, I'll leave it up to you to verify that these are, in fact, closed subvarieties of the Grassmannian. Sigma 2 will be the set of planes lambda that contain the point P, and sigma 1, 1 will be the set of planes lambda that are contained in the plane H. Notice that these are each isomorphic to P2. the lines through a given point, through the point P, are parameterized by a P2, and the lines in a plane, H, are parameterized by the dual projective plane. Now I want to do one more, if you like. Sigma 2, 1 will be the set of lambda, such that P is, that lambda both contains P and lies in H. And that, if you think about it, is just isomorphic to P1. It's just a set of the pencil of lines in a plane through a point. And if you want to be really fussy, I should write sigma 2, 2 is the set consisting of L itself, L alone. It's just a single point. And I could write sigma 0 as the whole Grassmannian. And I have the obvious inclusion relations here. I have the Grassmannian, G13, I'll just call it G for short, contains the cycle sigma 1, which in turn contains the cycles sigma 2 and sigma 1, 1 that intersect in the cycle sigma 2, 1, and then I have the cycle sigma 2, 2, or just a single point. And if you think about it also, I mean, again, we said that the Grassmannian has dimension 4. Sigma 1 has dimension 3. As we said, it's a hyperplane section, but you can also see it directly. Sigma 2 and sigma 1, 1 are both planes. We said they're isomorphic to P2. Sigma 2, 1 is dimension 1. A point is dimension 0. So these are my cycles. There's one in each dimension except for the middle dimension 2 where there are 2 cycles. Okay. Let's see how we're doing on time. Okay. So let me take a moment before we launch. I mean, so I'm going to say in a moment, in fact, I already said, that the classes of these cycles, I'm going to write the corresponding classes, the class of the cycle sigma 1 as lowercase sigma 1. And that's a sort of common convention. A cycle represented by a capital letter and denote its class by a corresponding lowercase letter. Likewise, I don't have to write all these down. Sigma 1, 1, class is sigma 1, 1, and so on. And these belong to the various graded pieces of the chow. This is codimension 1, so that's an A upper 1. This is codimension 2, and so on. So the claim is that these guys are an additive basis for the chow groups. And the problem now is to find all the intersection products. But let me just say for a moment how we know that. Is an interesting, and it's sort of something you could think about, and you could probably write down if you had a half hour, an hour, you could write down a complete proof of the following fact. This is, I said in general you can't calculate chow groups, but there's one sort of special circumstance where you can, and that is what obtains here. This is, and this is something I'm just going to show you in one case, this is an affine stratification. In other words, this is a stratification of the Grassmannian. If I take in each case, the complement of the substrata of a given stratum, it is affine, not just an affine right, but affine space itself. So for example, if I look at the cycle, sigma 1, and I take away the two subrights, the two substrata contained in sigma 1, so I take away sigma 2 union sigma 1, 1, this is isomorphic to A3. And, well, the others, in fact, are some simpler. See, if I take sigma 2, and I take away sigma 2, 1, that's isomorphic to A2. That's, for example, we can see sigma 2 is just the lines in 3 space through this point. If I remove the lines that happen to lie in a plane, I get lines through the point P not lying in a particular plane. That's just the complement of a line in P2. It's an affine plane. So I'm not going to go through each of these. You can do these very straightforwardly in coordinates, or you can write down very simply a map of associating to a line in this subset a point in 3 space. We can, if we have time, we can do this, but I want to move on. The point is, when we have an affine stratification of a variety, and again, that's a stratification such that the open strata are isomorphic to affine spaces. The classes of the closed strata generate the Chow. So let's give the variety a name X in general, and I'm saying that the classes of the closed strata generate the Chow. And what I'm saying basically is that any cycle in such a space can be deformed, specialized to one that is simply a linear combination of these closed strata. And it's not even hard to see how that works. If you have a cycle, for example, that lives in A3, as it meets A3, for example, meets this lies in the stratum sigma 1, but is, say, a proper subvariety of sigma 1. If it's not contained in sigma 2 a union sigma 1, 1, in other words, if it meets the A3, we can look at the open subset where it meets A3, and we can choose an origin in A3 away from it and just project it out, multiplied by T, to get a family of varieties, subvarieties of the Grassmannian, parameterized by T, whose original member is just the variety we started with, and when T goes to infinity, what we see is we don't know what we get, but it's supported on the complement to this A3 in sigma 1. So it's a linear combination, it's sitting inside sigma 2 union sigma 1, 1. In this way, we can keep pushing it out until it's actually equal to a linear combination of these strata. This is a process that works whenever we have an affine stratification. Yeah, of course, at this point you could say, well, how likely is it that we have an affine stratification? I mean, among all varieties, those that actually have an affine stratification are extremely, I mean, it's a very small subclass, I mean, of rational varieties. Of course, to have an affine stratification, in particular, means it has an affine open subset isomorphic to affine space. That means it's rational. Rational varieties are a tiny, tiny class of varieties. And among rational varieties, those with affine stratifications are even a smaller subset. So why am I even bothering to write down this statement? The reality is that while varieties with an affine stratification are a very, very small subset of all varieties, they're a fairly large subset of all varieties whose Chow groups we can calculate. So in fact, this statement is really quite useful in calculating Chow groups.
Sorry.
Yeah.
When you say that the classes of the closed strata generate A of X,
yeah.
You mean generate as a ring?
As a group. As a group. Yeah, so they form an additive basis for Chow. No, absolutely, absolutely. Now, in fact, I'm only going to be using the fact that they generate, which is the part you can prove by elementary methods. In fact, it's also true they generated freely, but that's a harder fact to establish. We don't need it because we'll see that these are independent classes when we work out the intersection products. All right, let me leave this up here, since we're going to be using these definitions. And let's start fresh on this. So, before we go on, any questions? I won't threaten you with my getting angry, but I do appreciate questions. All right, let's calculate intersection products. I should tell you, by the way, that the first 5 of these are completely elementary, and the 6th is interesting. Well, I mean, they're all interesting, but they're not exactly tough. Let's start with cycles in complementary dimension. Suppose I take take the intersection of sigma 2 with sigma 2. So what is that? Well, sigma 2 is the set of lines meeting, passing through a given point. Okay. And I want to intersect it with itself. Well, what that means is, in our view of the world, is that we need to find another cycle which is rationally equivalent to the original cycle, sigma, capital sigma 2, but which intersects it transversely. Well, again, if the class of the cycle capital sigma 2 doesn't depend on the particular point. Sometimes we even write the cycle as sigma 2 of P to denote its dependence on the point. This is lines passing through the point P, but the class of the cycle doesn't depend on P. If I chose, again, a different point, I could interpolate between those 2 points with a rationally parametrized family, and I would get a corresponding rationally parametrized family of cycles, so they're all rationally equivalent. So if I want to choose another cycle rationally equivalent to this one, but meeting it transversely, all I have to do is pick another point. And what I want to say is, okay, so I'll take another point, P prime, and now I'm going to just look at the intersection, count the number of points of intersection of these 2 cycles. Well, this is one I think we can all agree on. I'm looking at lines that contain P and contain P prime. How many of them are there? There's 1. So that's the first thing. Now, by the way, I'm writing 1 here. I shouldn't write 1. This is the class of a point. But here, I'm implicitly invoking the fact that we have a degree map from A0, 0-dimensional cycles on the Grassmannian, to Z. And that map, in fact, in this case, is going to turn out to be an isomorphism. Because we see that we have an affine stratification with just 1 0-dimensional stratum. That tells me that the Chow's group in dimension 0 is just Z. It's just freely generated by the class of a point. So when I write 1 here, I'm implicitly invoking this isomorphism. This is really, I should say, 1 times the class of a point. But that gets burdensome quickly. So we're just going to accept that the right-hand side, we're just going to write numbers. All right, here's another one. What about sigma 11 dot sigma 11? Well, it's the same thing. Sigma 11 is lines lying in a plane H. If I want to intersect that class with itself, I just choose another plane. This is sigma 11 of H intersects sigma 11 of H prime for another choice of plane. And the question is, how many lines lie in both H and H prime? Well, if I take 2 general planes in P3, they have one line in common, their intersection. So this is, again, 1. Okay, you guys do this one. Sigma 2 dot sigma 11. Want lines that pass through a general point P and lie in a general plane H. How many? You're shaking your head. Does that mean? What's the answer? 0. Yeah. So that's it. Now, by the way, notice. I'm going to notice that we've now proved something already, which is that these 2 classes, sigma 2 and sigma 11, are independent. That's what I meant when I said that we don't need the statement here that these generate freely. We can establish the independence by writing down the intersection matrix. The intersection matrix is just the identity matrix. Since that's non-singular, it follows that sigma 2 and sigma 11 are linearly independent. So the independence is going to fall out of the calculation of intersection products. Okay, a couple more. Actually, just one more for the moment. Sigma 1 dot sigma 2 1. So now we're looking at lines that meet a line L. They lie in another plane, H prime, and pass through a point P prime in that plane. So we're looking, sigma 2 1 here is the set of lines in the plane H prime through the point P prime, how many of them will meet L? One. I mean, L, see, I've drawn it misleadingly. L, in fact, will meet H prime in a point, as any line must meet a general plane. And if I call that point Q, the only line that satisfies all these conditions is the line joining Q to P prime. So this is just one. And this accounts for all intersections in complementary dimension. These are all the intersections that are zero dimensional. So now we have a couple more to do that are not in complementary dimension. Let's try those. Let's do sigma 1 dot sigma 2. So let me draw the picture. Unless it's sort of obvious already. Sigma 1 is just lines meeting a given line L, and sigma 2 is lines containing a point P prime. Now again, this is lines meeting L is codimension 1. Lines passing through the point P prime are codimension 2. So we expect something of codimension 3. We expect a curve here. What do we see? Well, that's exactly what we see. The lines that meet L and pass through P prime necessarily lie in the plane spanned by those. And so this forms exactly a cycle sigma 2, 1. It forms sigma 2, 1. And likewise, if I take sigma 1 dot sigma 1, 1, that's lines meeting L and lying in a plane H. So this time I won't try to mislead you. I'll draw the plane H prime so that it meets L. The lines that lie in H prime and meet L, again, form the pencil of lines in H prime passing through the point of intersection. So that's, again, sigma 2, 1. All right, so now we come to I promised you an interesting example, and now we come to that part. And this is the crux, the one that is not immediately obvious, though there will be many ways of arriving at this. See, we've been lucky so far. Every time we've had a product of classes to calculate, we've been able to find representative cycles for those classes whose intersection just happens to be another one of these Schubert cycles, another one of these closed strata. Now, I want to do the one remaining case. What's the one remaining intersection property we haven't calculated? Sigma 1 squared. And I want to do that. And now we see that the honeymoon is over, so to speak. If I want to do sigma 1 squared, that's the class of the locus of lines that meet a line L and meet a line L prime. So let me draw the canonical picture here. In this case, just consists of two lines. We have a line L and another line L prime. They're general. So in particular, they're skewed to one another. And we're looking for the set of lines meeting both. Now that's visibly a surface. And you can check that the intersection is transverse. But it's not a Schubert cycle. It's not visibly a linear combination of the cycles sigma 2 and sigma 1, 1 that we have said generally. So how do we calculate this class? Well, the answer is, it's kind of a cute process. We haven't exhausted the power of linear algebra quite yet. What we do is we say, look, we don't know what this class is a priori. But what we do know is that it is a linear combination of our two generators. In other words, we can necessarily write this as A times sigma 2 plus B times sigma 1, 1 for some pair of integers, A and B. The question is simply, what are the integers A and B? And to find the answer to that, to find, let's say, for example, A, we take this equality and we intersect on both sides with the cycle sigma 2. So what do we see? What we see is that sigma 1 squared times sigma 2, well, we know how to intersect the right-hand side with sigma 2. As we said over there, sigma 2 dot sigma 1, 1 is 0. That term goes away, and sigma 2 squared is just 1. So this is just A. Now, how do we evaluate this? Well, we draw the picture again. Because again, we can find representative cycles here, and we can actually describe the intersection. So let me draw the picture. We have sigma 1 squared is lines meeting L and lines meeting L prime, right? Now, I want to take lines passing through a point, another point chosen generically with respect to these. So now I'm asking this: if I have, in general, 2 lines and a point in 3 space, how many lines pass through that point and meet both lines? 1. And there are many ways to see that. Think about it this way. If a line meets L and passes through P double prime, it has to lie in the plane spanned by L and P double prime. Likewise, if it meets L prime and passes through this point, it has to lie in the plane spanned by those. And so, in fact, it can only be the line of intersection of those 2 planes. Yeah?
Can't you use associative?
Yes, we can. Yes, absolutely. As I said, there's many ways of doing this. And in fact, the comment is absolutely well taken. I could also say that sigma 1 squared dot sigma 2 is sigma 1 times sigma 1 sigma 2, which is sigma 1 times sigma 2 1, which is 1 already. Absolutely. So the conclusion in any case is that A is equal to 1. And we can play the same game with, to find B, we intersect with the cycle sigma 1, 1. And again, that, when we look on the right, that has the effect of eliminating this term, because the intersection product is 0, and gives us, just returns the value B. So what we get is that B is just the product sigma 1 squared times sigma 1, 1. And that's, you can also do this way. You can just re-parenthesize this product, this triple product, and use what we've already calculated. Or we could just do it again directly by saying, if we have 2 lines L and L prime, and a plane H double prime, well, the number of lines that lie in H, or H double prime, and meet both lines, there's just the 1 line joining the points of intersection. So either way, we get 1, and now we've finished our calculation. The conclusion is that A and B are each 1, and we can complete this list of products by saying that sigma 1 squared is equal to sigma 1, 1 plus sigma 2. All right. All right, good. We're right on time. Now we can answer the question. Remember what we said, the 4 steps in the paradigm. Introduce a parameter space. We did that. That's the Grassmann, right? Calculate the Chow group, or Chow ring, I should say, of that parameter space. We just finished doing that. The 3rd step was identify the class in that Chow group, or Chow ring, of the cycles we're trying to intersect. Now here, in fact, we've been working with it all along. We're looking at the cycle of lines meeting L1, the cycle of lines meeting L2, the cycle of lines meeting L3, and the cycle of lines meeting L4. They each have class, what we've been calling sigma 1. And so the final step, when we evaluate, we count the number of points of intersection by calculating the product of those classes in the parameter space, in the Grassmannian. Well, the answer to the first question, at least, is simply sigma 1 to the 4. And now we can, again, there's many ways of doing this, but I'm just going to write it as sigma 2 plus sigma 1, 1 quantity squared. The cross term is 0, and we get the answer 2. So the answer to the question is there are 2 lines meeting each of 4 lines. Now, that was not worth an hour of your time, or even 50 minutes. If you really wanted to know the answer to that question, I said there were lots of ways of doing that. One way is to say, well, look at the set of lines meeting the first 3. And if you think about it, this is a nice exercise. If you take 3 random lines, 3 pairwise skew lines in 3 space, the set of lines meeting all 3 form the ruling of a quadric surface, a ruling of a quadric surface. Then the 4th line meets that quadric surface in 2 points, and there's 1 line of the ruling for each of those 2 points, so you get the number 2. That's a lot less than 50 minutes, even if I should have maybe said that a little bit slower. But you could find your own solutions to this. But now let's take a look at the second part. I just want to do this one and then we'll be done. For the day, anyway. How about the twisted cubics? They're not just there because Robin proposed in principle that we should have them. It's a good illustration because the one thing we did not see in this particular problem is the 3rd step. Namely, as I said, we calculated the Chow group, or the Chow ring of the Grassmannium, but then it turned out that the cycles we were intersecting were actually the generators of the Chow group. We didn't have to calculate their classes. So now we'll do the same problem for the twisted cubics. So now step 3 is to find, well, I'll tell you what, let's let sigma of C be the set of lines meeting a given twisted cubic. So C is a twisted cubic, and we're looking at the set of lines meeting that twisted cubic. And I want to calculate the class. So the first step, step 3, is to find the class, I'm just going to call it sigma, of this cycle. What's the dimension of that cycle? We should ask that first. How many lines, dimensionally, how many lines meet a twisted cubic? That's not hard. I mean, basically, you could say, for example, that for every point on the twisted cubic, there's a 2-parameter family of lines passing through that point, and you have a 1-parameter family of points, so it's a 3-dimensional variety. That means, in particular, this class is going to live in A1 of G. And how do we find its class? Well, we use the same method we used to calculate sigma 1 squared. We say, the one thing we know, we can write sigma is some multiple of sigma 1. That's the generator of the Chow group in codimension 1. How do we calculate A? We intersect both sides with the cycle, there's no choice here, in complementary dimension, in sigma 2, 1. On the one side, sigma 1 dot sigma 2, 1 is just 1. So the conclusion is that A, the coefficient, is just the intersection number of this class sigma with sigma 2, 1. That is simply the number of lines, lambda, such that to satisfy 2 conditions, lambda intersect C is non-empty. So that's the cycle sigma of C here. And lambda satisfies the condition of sigma 2, 1. In other words, P is in lambda is in H. So for the last time today, I will draw a picture. What we have here is a twisted cubic curve, C in 3 space. We have a plane H. Again, since that's general, we're going to say it's a plane that's going to meet the twisted cubic in 3 points. And then we have a point in that plane, P. Put it right here. How many lines, we're asking, pass through the point P, lie in the plane H, and meet the curve C? Well, 3. I mean, if it lies in the plane H, it passes through the point P. it lies in the plane H and meets C, it can meet C only at one of the 3 points of intersection of C with H. And of course, if it passes through one of those points and passes through P, it must be the line joining P to one of those 3 points. So there's 3 lines. And the conclusion is, finally, that, I guess I'll just erase this, because we now know the intersection products. We should. So what we conclude is that, and this is, again, step 3 in our paradigm, that the class sigma of C, or what we're calling class sigma, is just 3 times sigma 1. And so the answer to part 2 is that the cardinality of the intersection of sigma of Ci, I was 1 up to 4. So now we're intersecting, we have 4 twisted cubics. We want to know how many lines meet all 4. Well, we're intersecting the corresponding cycles in the Grassmannian. We just take the product of their classes. That's 3 sigma 1 to the 4th power. And that, if I'm not mistaken, is 162. Is that right? Yeah, okay. And that's the answer to the second part. And that's a little less easy to visualize than the first one. And this is very typical of the sort of problems in enumerative geometry. It's not so much the answer. I mean, no one is likely to come up to you on the street and ask you how many lines there are that meet 4 general cubic curves. But I think it's the satisfaction of knowing that you can calculate that. So that's going to do it for us for today. Next time, tomorrow,